So therefore, this carbon is not chiral, where it is asymmetric or chiral. So it is not chiral. So that's the question there. So let's go to the dipolar structure. I also mentioned this before. When I indicate that the structure of an amino acid contains a positive charge actually in the amino group and a negative charge in the COO. So therefore, it is dipolar. We have two targets, and because when amino acids occur in a solution, we know that amino acids are repeating units of proteins. So our protein can contain a mixture of these neutral, acidic, and basic amino acids. Although there are some proteins which may contain more of the acidic amino acids. And for example, hexone, which is the protein that is found in nucleic acid, combined with nucleic acid to form new proteins, they are usually basic, so they contain more basic amino acids. So when they are already in a source of protein, they will of course have a certain IPA. What is IPA? So look at your notes and chemical history. That is the pH at which the numbers of positive and negative charges in a large sample. The large sample here is this, the amino acids that are found in a protein molecule, are equal, and an amino acid exists predominantly in its neutral dipolar form, and we call that phase of the IPA or isoelectric point. So, although we haven't studied yet the structure of the fifth peptide, but knowing that the repeating units of proteins are amino acids, so we know that it consists of a mixture of these acidic and basic amino acids. So just like our example, the basic amino acids are lysine, arginine, and histidine. If you look at the structure of lysine and histidine and arginine, like example lysine, you have on the gamma carbon, the last carbon there in the R group, we have an NH3. Therefore, it is carrying an extra positive charge. While in an aspartic acid, it will carry an extra negative charge. So therefore, when you have that in the mixture of these amino acids in the protein molecule, so it will now change the overall number of positive and negative charges. But eventually, when they are already in a mixture, there is a certain pH that we have the number of positive charges will be equal to the number of negative charges. That is why it is what we call as an IPA. So later on in our experiments in proteins, we will be experimenting IPA. So we will know, like for example, casein. So casein is a protein that is found in milk. Or we call it, this place one of the cereal, or kettle, or cheese, in English. So this of course is found in milk. And casein is of course, biochemistry contains specifically or protein in the milk, because at that certain pH of milk, which is about 6 point something, 6 point, I think 6.2, So that means of course the pH there is away from the IPH of the state. The IPH is contained 4.7. that is interesting. So this is the point where it is electrically neutral, and that is the time that the thing will precipitate. Just like when you add, have you noticed that when you add vinegar to your milk, it will sort of run coagulate. That is actually the surface being the IPH, the pH is very near to its IPH. So we will go to that later. So when we really start the reaction. But that is what we mean by IPH. That is the point at which the amino acids that are found in the protein molecule is at its IPH, that means it's electrically neutral. So the numbers of positive and negative charges are equal. And at that time also, or at that point also, the protein becomes insoluble. So that is why you will be noticing that it is precipitating. It becomes insoluble. And that is one method of preparing the seed. That is let's say of different brands of cheese in the market. That is how they prepare. And they are being prepared by adding over acid, or maybe they can also use enzymes to precipitate or to isolate the protein. So let's go to within the metronome considering there is a general structure there that is showing us the predominant form of a certain amino acid at low pH. We say low pH acidic. So when it is acidic, what will happen to the structure there? To the structure. That will, of course, so the amino acid will now carry, you added acid, so it will now attract the oxygen here, so becoming a positively charged amino acid. That is now the predominant form. If you make the amino acid solution in acidic condition, well, at basic pH, that is high pH, what will happen? The base or honey becomes no longer positively charged, and this is now the predominant form of the amino acid is you place it in basic condition. So by the way, add our group, because it is if I may, I will be asking you in the examination, is this the predominant form of alanine in basic condition or basic pH? And this is already alanine. So you just think with the R group. So let's go to the uncommon amino acids. When we say uncommon, we know already that the repeating units of amino acids are alpha amino acids, and they are uncommon because they are only present in a certain protein. Like hydroxylizing and hydroxyprotein, these are only present in collagen and gelatin. They are not present in other proteins. Thyroxine and 3' 5 like iodothyronine, these are of course the hormones that are found iodinated, and of course produced by the thyroid gland. So, thyroglobin. No R there, thyroglobin. Then methyl hepcidin and epsilon N methylysine, epsilon NNN trimethylysine. These are oxyglutamic acids is found only in proteins that are involved in blood clotting. Protein. Then N-methylarginine and N-acetylysine